The paper discusses the issue of finite element solutions not converging to the true solution on triangular and tetrahedral meshes that violate the maximum angle condition. This problem was first identified by Babushka and Aziz in their work 4, which showed that standard conforming, nonconforming, and discontinuous Galerkin finite elements do not converge as the mesh size approaches zero. To illustrate this problem, the authors provide two examples from calculus. In the first example, a circle is approximated by polygons, and as the longest edge of the polygon goes to zero, the arc length of the polygon converges to the circumference of the circle. However, in the second example, a cylinder is approximated by linear triangles with both horizontal and vertical sizes approaching zero. Despite the distance between the cylinder and the triangles decreasing to zero, the total area of the triangles converges to a different number than the surface area of the cylinder. This discrepancy occurs because the small triangles maintain an angle to the cylinder, failing to approach the tangent planes to the surface. The authors then introduce a type of finite element called nonconforming finite elements, which have functions continuous up to the pk1 order. These elements are L2 orthogonal to the space of pk1 polynomials on the edge. When applied to the cylinder approximation problem, this method involves p1 interpolation at 3 mid-edge points instead of the 3 vertex points. Although this method provides a slightly better approximation, the problem remains unresolved as the area of the triangles still does not converge to the area of the cylinder. Similarly, nonconforming finite element solutions do not converge to the true solution on such meshes. However, the authors propose a solution to the cylinder approximation problem by moving the 3 interpolation points toward the center, resulting in secant triangles that become almost tangent to the cylinder. Alternatively, using the closest triangles on the mesh, i.e., the P1L2 projection of the cylinder function, would also cause the total area of the triangles to converge to the area of the cylinder. The paper concludes that the weak Galerkin finite element method converges on triangular and tetrahedral meshes violating the maximum angle condition, i.e., on arbitrary meshes. This convergence is confirmed through numerical tests. In the context of finite element methods, this research explores the development of a weak Galerkin (WG) finite element method that can guarantee convergence on arbitrary triangular or tetrahedral meshes, without any condition. This is achieved by introducing a novel gradient-preserving Zhang transformation, which is a scalar version of the inverse, divergence-preserving, Piola transformation. The WG finite element space is defined as VH equals V0, VB, V0 element of L2, TH, V0, T element of PK, T, VB element of L2, EH, VB, E element of PK plus 1, E, VB, partial differential omega equals 0, where pk, t, denotes the space of polynomials of degree k or less on T. The weak gradient for generalized functions in VH is defined by nabla WVH, Q, T equals V0. Nabla dot operator Q, T plus n airy summation E element of partial differential TVB, Q dot operator NE, for all Q element of pk plus 1, T, D, where D equals 2 or 3, the space dimension, and n is the outer unit vector on E subset of partial differential T. By an integration by parts, the definition can be rewritten as nabla WVH nabla V0, Q, T equals VB V0, Q dot operator NT, for all Q element of pk plus 1, T, D. The model problem of Poisson's equation is considered. Increment U equals F in omega. U equals 0 on partial differential omega. The finite element approximation problem reads: find a element of VH such that nabla WVH equals F VH for all VH element of VH. The key result of this research is that for all VH equals V0 VB element of VH, it holds that parallel nabla V0 parallel 0 is less than or equal to C parallel nabla WVH parallel 0, where C greater than 0 is independent of the shape regularity and the size of TH. Parallel dot operator parallel 0 is the L2 norm, and nabla W is defined in 2.2. This result is proven by decomposing VH on the unit reference triangle or tetrahedron T into V1 plus V2 element of V1, T, plus V2, T, where V1, T, and V2, T, are the subspaces of VH. The analysis is different from the typical error estimate in the finite element method, as the interelement error is converted to other errors inside elements. Local interpolation and projection are introduced directly to the error estimation of the H1 projection, while they are typically used to show the subspace has the required global approximation property only. A gradient-preserving Zhang transformation is defined, which is like a scalar version of the inverse, divergence-preserving, Piola transformation. This transformation is crucial for the convergence of the WG finite element method on arbitrary meshes. The work is significant in mathematics, as it is the first time ever we can guarantee the convergence of finite element solutions on meshes without any condition. Here is a combined summary of pages 5 and 6 of the research paper. The authors introduce a finite element method for solving the Poisson equation, focusing on the construction of a gradient-preserving transformation, known as the Zhang transformation. This transformation, denoted by equation 2.8, maps functions from a general triangle or tetrahedron to a reference element, preserving the gradient. The authors prove lemma 2.1, which establishes a lower bound for the norm of the gradient of a function, and lemma 2.2, which ensures the uniqueness of the solution to the linear system of finite element equations. The proofs of these lemmas involve the use of the Zhang transformation, the definition of the weak gradient, and the properties of the finite element spaces. Specifically, the authors employ the affine mapping F, the Jacobi matrix J, F, and the constant matrix M to establish the gradient-preserving property. Moving on to the convergence analysis, the authors present theorem 3.1, which provides an error estimate for the finite element solution. The theorem states that the error between the exact solution and the finite element solution, measured in terms of the L2 norm and the H1 seminorm, is bounded by Ch(k) plus 3, where H is the mesh size and K is the polynomial degree. The proof of theorem 3.1 involves testing the Poisson equation with a function from the finite element space, applying integration by parts, and using the definition of the weak gradient. The authors also employ the local L2 projection operator QH and the L2 projection operator πk plus 1 to establish the error estimate. The final result, equation 3.4, provides a bound for the error in terms of the mesh size and the regularity of the exact solution. This research paper discusses the development of a novel finite element method for solving elliptic problems, focusing on the analysis of the interpolation error estimates and the numerical test results. The finite element method is based on the BDM interpolation, which is used to approximate the gradient of a function in the H-div space. The authors introduce the BDM interpolation operator IBDM, defined by three conditions. The first one involves the L2 projection of the function onto the space of polynomials. The second one is related to the boundary conditions, and the third one ensures that the divergence of the interpolated function is preserved. The key result in this section is the interpolation error estimate, where the authors show that the difference between the interpolated gradient and the true gradient can be bounded by the size of the element and the Sobolev norm of the function. In the numerical test section, the authors solve a 2D and a 3D Poisson's equation with a known exact solution. They use two families of meshes, one quasi-uniform and another degenerate, violating the maximum angle condition as the mesh size decreases. The results are presented in Table 1, showing that the P1 conforming finite element method converges at the optimal order in L2 norm and is superconvergent in SEMA 1 norm on the quasi-uniform meshes. However, when refining the mesh more in one direction, the solutions do not converge at all and instead converge to a different function, as seen in the second half of Table 1. This indicates that the P1 conforming finite element solutions do not perform well under non-uniform refinement. The research paper discusses the performance of two types of finite element methods, P1 conforming and P1 weak Galerkin, in solving Poisson's equation on both 2D and 3D domains. The authors present error profiles for these methods, comparing their convergence rates on different mesh configurations. In the 2D case, The P1 conforming finite element method exhibits optimal convergence in L2 norm and superconvergence in SEMA 1 norm on quasi-uniform meshes, as shown in Table 1. However, when refining the mesh more in one direction, the solutions do not converge at all, indicating a lack of robustness in this method. On the other hand, the P1 weak Galerkin finite element method demonstrates superior performance, achieving 2 orders above the optimal convergence rate in both L2 and SEMA 1 norms on both quasi-uniform and degenerate meshes, as presented in Table 2. This suggests that the weak Galerkin method is more robust and efficient than the conforming method, particularly in handling non-uniform mesh refinements. The paper also extends its analysis to the 3D case, where the P1 conforming finite element method shows suboptimal convergence rates on both quasi-uniform and degenerate meshes, as indicated in Table 3. In contrast, the P1 weak Galerkin finite element method maintains its superior performance, achieving 2 orders above the optimal convergence rate in both L2 and SEMA 1 norms on both types of meshes, as detailed in Table 4. The results highlight the advantages of the weak Galerkin method over the conforming method, especially in terms of robustness and efficiency. The authors provide visual representations of the meshes used in their experiments in Figures 2 and 3, illustrating the differences between quasi-uniform and degenerate mesh configurations. Overall, the study contributes to the understanding of finite element methods' performance in solving elliptic problems, emphasizing the importance of choosing appropriate numerical methods for specific problem domains and mesh configurations. The findings could potentially guide future research in developing more efficient and robust numerical methods for various applications. The finite element method presented exhibits 2-order superconvergence in both L2 norm and energy norm on quasi-uniform and degenerate meshes, as demonstrated in Figure 3. The error profile for the 3D P1 weak Galerkin finite element is presented in Table 4, showcasing the method's accuracy in computing the solution. The table displays the error norms for the solution and its gradient, with the corresponding convergence rates. The method's performance is attributed to the weak Galerkin finite element formulation, which allows for the use of discontinuous elements. The formulation is based on the concept of weak Galerkin, which involves the use of a stabilizer-free approach. This approach enables the method to achieve superconvergence, as demonstrated in the numerical results. The authors also provide a comprehensive list of references, citing relevant works in the field of finite element methods. The references include works on discontinuous Galerkin methods, nonconforming elements, and weak Galerkin methods. The authors also acknowledge the support of the China Natural National Science Foundation and the National Key R&D Program of China. The paper concludes with a statement on the originality of the work, compliance with ethical standards, and the availability of supporting data. The authors declare that they have no potential conflict of interest and provide their email addresses for correspondence. The references provided demonstrate the authors' thorough understanding of the field and their commitment to advancing the state-of-the-art in finite element methods. The paper's technical content is supported by a rigorous mathematical framework, ensuring the accuracy and reliability of the results. The use of weak Galerkin finite element methods has far-reaching implications for the solution of partial differential equations, and this work contributes significantly to the field. The numerical results presented in the paper demonstrate the method's effectiveness in achieving superconvergence on various meshes. The error norms and convergence rates presented in Table 4 provide a clear understanding of the method's performance. The paper's technical content, combined with the comprehensive list of references, make it a valuable contribution to the field of finite element methods.